Tuesday, we talked about intermolecular forces, IMFs, intermolecular forces. We talked about van der Waals, dipole-dipole interactions, and hydrogen bonding. After that, we switched over. We said, okay, we're going to focus on gases now. So there's three kinds of properties we use to measure and learn about the behavior of gases. The first one we're talking about is pressure. And there's a bazillion units for pressure. Okay, so we had the PSI was one. Then we introduced the atmosphere, ATM. So we said 1 ATM is equal to almost 15 PSI, 14.7 pounds per square inch. And then we introduced millimeters of mercury. The nickname for millimeters of mercury is a torr. Just they honored the guy who came up with it. So there's the relationships for that. I'm going to introduce the last one, and then we're going to do a conversion problem, just so you're a little bit more comfortable with these units. This is the SI unit. So remember, there's an international system of units, and the purpose for that is articles and research in medicine. It's nice to have an international system where all countries agree on the size of certain units. So that is the Pascal. Okay, it's called the Pascal, PA. So 1 ATM is pascals are really, really, really small. Okay, so it's 101,325 pascals is 1 ATM. Okay. You can also convert that to kilopascals. So you divide by 1,000, right? It'd be 101.325 kilopascals would be 1 ATM. So here's essentially, in a nutshell, what I want you to know regarding units of pressure. Okay, I want you to know that 1 ATM is equivalent to 760 millimeters mercury. It's equivalent to 101,325 pascals and 14.7 psi. Okay, don't worry about torrs or kilopascals. All right, so we're going to do one quick conversion problem. We were talking about tire pressure. You guys had all kinds of stories with your tires, all kinds of vehicle mishaps Tuesday. I'm sure I didn't even hear all of them. Okay, what is this in millimeters of mercury, pascals, and atmosphere? Okay, so we're just gonna, there's two different ways you could do this. You could take 34 psi every single time and convert to those individual units, or you can just continue one at a time, convert to millimeters of mercury, and then go straight from millimeters of mercury to pascals, and then straight to atmospheres.
Can you go back up, like, just right quick? Right there.
Yeah, I'm going to be scrolling up to this quite a bit, Glenn, in the next few minutes, because we're going to use this information up here a lot. All right, so start with 34 psi. Yeah, I'll be right back up to that. 34 psi. And first question is, how many millimeters of mercury is this? Okay, well, we know, let's go back up. 760 millimeters of mercury is equal to 14.7 psi. That's a conversion factor. So I want to cancel psi, convert to millimeters of mercury. These are one-step conversions. So 14.7 psi and 760 millimeters mercury. All right. So I need you guys to help me out. 34 times 760, but divided by 14.7 is how many millimeters of mercury? So like around 1700, yeah. 1757.8. Okay. So there's that. Now we're going to convert this. I'm going to go straight to pascals. I know, let me go back up, that 101,325 pascals is equal to 760 millimeters of mercury. So now I'm going to grab those two numbers in units and cancel millimeters of mercury, convert to pascals. So I want millimeters of mercury on bottom. 700, and for every 760 millimeters of mercury, we get 101,325 PA. So it should be a really, really big number because, again, pascals are the smallest unit. So it takes a lot more of them to be equivalent to the other units. Anybody got it? Do 1757.8 times the 101,325. Divide that by 760. Kristen says she got, okay, Chris got the same thing. So 234,000. So this equals 234,354.1, and this is pascals. And then lastly, if we were going to figure out, okay, how many ATM is this? How many atmospheres? We need to go grab those two numbers. Okay, so this time I want 1 ATM is 101,325 pascals. So I'm going to grab those two numbers in units, cancel pascals, convert to ATM. ATM's a nice unit, isn't it? I like the 1. So you just do the 234,354.1, divide that by your 101,325. And each time we see that first unit cancels. Okay, what do we got for ATM? 2.3. Very nice. Okay. So here's why we took a minute to introduce these units and these pressures. When we get to gas law problems, there may be times where you're given units of pressure and you see two different units. Okay. Kind of like, remember the delta G problems where you got kilocalories on delta H and calories on delta S, and you had to make sure they match. Okay, you had to convert the delta S to kilocalories. Same idea here. When we get to these gas laws, if you got two spots where you put pressure in, you're going to see in a minute, you got to make sure the units match. Everything needs to be in, ATM or PSI or whatever. Just make sure they match. So that's why we took a minute to practice a conversion like this. All right, questions on what we just did, on how any of these units relate? I think this is a key slide. Just have that available so that you have all those numbers there. Don't spend time trying to memorize all these. Man, people in the fall are really going to have it in. Don't tell your friends that all my exams are open note, open book, because they won't be in the fall. Usually they're not. Okay, moving on to gas laws. Combined gas law. Combined gas law. So, as we mentioned, pressure, volume, and temperature are ways we study gases. And over time, they realized there were certain relationships. Like, for example, if you have a container, okay, if you had a set container with gas in it, and it's at a certain volume and a certain pressure, okay, to keep pressure and volume kind of a constant there, if you increase the volume, what's going to happen to the pressure of the gas inside? If you have the same amount of gas, the pressure decreases, okay? If you decrease the volume, what's going to happen to the pressure inside? Okay, you're compressing the gas, so the pressure increases, all right? So we learn certain relationships, like the fact that pressure and volume kind of work oppositely, okay? If you have the same amount of gas, as you increase volume, you decrease pressure, all right? Or as you decrease volume, you increase pressure, and vice versa. So as we learn things like this about gases, they put together this combined gas law. This combined gas law is the compilation of 3 simple laws that you've probably heard of in a previous science class, possibly. Boyle's law, Charles' law, Gay-Lussac's law. Okay, so here's the combined gas law, and it's this: P1 V1 over T1 equals P2 V2 over T2. Okay, I wish there was a fun song like the quadratic formula. Anybody learn the quadratic formula to a song? That's how my teacher talked to me. I still remember it because of that. I don't have a song for you for this, but there it is. Okay, and this helps us determine changes in gases' physical properties. And it obviously describes relationships between pressure, volume, and temperature and how these things change. Okay, because gases are constantly changing. They're reacting, especially in things like the atmosphere, which is gases, right? Okay, so there's the law, but we're going to break it down. I'm going to show you the 3 simple laws that were put together into this combined gas law. We're going to start with Boyle's law. Okay, so as you can see, the title of the slide, Boyle's law is the relationship strictly between pressure and volume. So when you're looking at a relationship between 2 of these 3 properties, The one that's not listed is held constant. Okay, so temperature here is being held constant. So we're essentially asking this question: what does the combined gas law look like when the temperature, I'm going to abbreviate temp, is held constant? So if we're not changing the temperature, what happens to gases when pressure or volume are manipulated? So that's Boyle's law. So imagine you're going to see this picture on the next like 3 or 4 slides. This is straight from your textbook as well if you want to go back and reference it there. You have this cylinder and it's got gas. The green is the gas inside the cylinder. And if you have a lid that is movable, okay, so kind of like a piston, if you could think about it like that, a movable lid. And we have inside, we have 1 liter of a gas. So that's the volume. All right. And then it's held at a pressure of 1 atm. 1 atm, 1 liter gas. Well, what if we increase the pressure? How could we do that? We just press down on the lid, right? Anybody ever tried to pump up your bike tire before with an air pump? Okay, so it's kind of like this, but you don't have the thing like set right, and you try to push down and like it won't go. Anybody? Anyway, so it's kind of that kind of scenario. But if we press down, what's going to happen is you're going to really pressurize that gas. Okay, you're decreasing the volume. If we cut the volume, we push down on the lid to where we now the size of the gas, the volume of that space is only half a liter. What did we do? If we have the same amount of gas in there and it's a constant temperature, now the pressure is going to be at 2 atm. So you see what happened? Volume was cut in half, pressure was doubled. Volume decreased, pressure increased. Okay, it works the opposite way too. If we pull out on this lid, volume increases, but pressure will decrease. So you see how they're opposites. Well, what we say because of that is that the relationship there, volume and pressure, they are inversely proportional. So we say, maybe you've seen this kind of notation before. This is, don't worry about this too much. I'm not going to put something like this directly on the exam, but P and then they do the squiggle is related to 1 over V. That means they're inversely proportional. If P was directly proportional to V, then you would just say P squiggle V. Okay, but it's 1 over V. They're inversely proportional. As one increases, the other decreases. So when you multiply these two together, you always get a constant. Check yourself, okay? What is on this side? 1 times 1 is just 1. That's the pressure and the volume condition on that side. Are we going to get the same number on the other side? The pressure is 2 times 0.5. Yep, that equals 1. So when you have gas held at constant temperature at certain pressure volume conditions, that relationship there, as one changes, the other inversely changes. And you always get a constant when you multiply those conditions together. Okay, this was the problem I was most excited about. This is the problem I was telling you. So this is a very good example of what I'm asking you to do for the bonus point opportunity. Okay, I cited my source right here. This is just from 2020 last year. So I thought that was kind of cool, pretty recent. Look at this, using Boyle's law, P1V1 equals P2V2, we can calculate the change in volume at different altitudes. Why would that be important? Well, many reasons, okay? Does anybody know somebody's ever tried to hike like Mount Everest? Intense hikers have to pay attention to this. Scuba divers have to pay attention to this kind of stuff, but it also plays into nursing. I'm going to show you how. For example, a patient with a simple pneumothorax. Okay, when I first read this, I was like, a hoodoo-wuddy, huh? A pneumothorax. Okay, this is a collapsed lung, essentially. All right, maybe you're familiar with this terminology. Is being airlifted. Okay, so they're being put in a helicopter to their local hospital. I mean, they really got to pay attention. Think about babies that are born with any kind of heart defect. If they're med flighted, I know friends who've had kiddos med flighted to hospital, very scary. But you had to pay attention to this kind of stuff, especially with teeny tiny lungs like that. Airlifted to their local hospital. They have a collapsed lung pneumothorax with a volume of 1,500 milliliters at sea level. Okay, which we know at sea level, it's 1 atm or the 101.3, it should be 0.325. Kilo, this is kilopascals. Okay, again, you don't have to worry about this. We could just say 101.325 pascals, same as 101.3 kilopascals. Okay, so at altitude, so let's say the helicopter reaches a kilometer above sea level. At 1 kilometer, at an altitude of 1 kilometer, the pressure is 90 kilopascals. Okay, so as you increase in elevation above sea level, the pressure decreases because you have less and less atmosphere pushing down on you, remember? So assuming the patient remains at a constant temperature, calculate the volume of the pneumothorax. So what happens to their lung the higher they fly in the helicopter? Okay, that's the concern here. So we're just going to plug these in and solve for what we don't have. So what do we have? I like to go through, by the way, on these kinds of problems and highlight what I have. I've got a volume here. So I'm going to call this V1. So we're going to write out, this is the first volume I'm given. That's why I'm calling it V1. V1 is 1,500 milliliters. How do I know it's a volume? Units of milliliters. Okay, at sea level, the first pressure that I'm given is 101.3 kilopascals. So again, you can work this in kilopascals or in pascals. We'll just work it in kilopascals. Shouldn't be any issue to do that. So that's P1. P1 is 101.3 kilopascals. Okay, then something changes at an altitude of 1 kilometer. Well, I'm not interested in the elevation necessarily, but I am interested in how the pressure changes at that elevation. So the pressure associated with that elevation is 90 kilopascals. So this is the second pressure I'm given. So that is P2. So P2 is not 90 kPa, right? So what happened? Pressure decreased. So what do you expect the second volume to be? We're looking for V2. Do you expect it to be, if pressure decreases, what's going to happen to volume? Remember, they're inverse.
Increase.
Increase. So that could be dangerous. We don't want the volume of the lung to increase too much. So let's figure out what it will be. So we just plug in. We got P1 V1 equals P2 V2. That's our equation. So we're just going to plug in. And what I noticed, you got to check my units match. If they gave it to me in like ATM, we'd have to convert. We need everything to be in the same units. So I don't care if you convert it all to ATM or whatever. Just make sure both your pressures, P1 and P2, are in the same units, and they are. So we're going to do 101.3 kPa times 1,500 milliliters. Again, here, if you're given milliliters and liters, make sure units match. We're looking for the second volume, so we're going to calculate it with units of milliliters. That's going to be equal to 90 kPa times V2. That's what this looks like. So we're going to solve for V2. So how do we solve for this? We've got to isolate V2. So I need to cross divide both sides by 90 kilopascals. And then that causes them to cancel on this side. So y'all help me out here. 101.3 times 1,500 divided by 90. Chris and Bailey, okay, good. 1688.3, and what are the units on this? This is a volume. Yep, thank you, Gabby. Milliliters. That is V2. So the higher you fly up, the larger and more that lung is going to expand. Okay, and that lung, you got to be careful with it. So you wouldn't want to fly too high. But anyways, I thought that was a cool application, okay? There's many more out there. So that's the kind of thing that I want you to look for. Moving on to Charles' law. This is a relationship between what? Temperature and volume. So what are we holding constant? This is what the combined gas law looks like when the pressure is held constant. I think I forgot to write Boyle's law up here on this slide, didn't I? P1 V1 equals P2 V2. Sorry, I meant to write that in. P1 V1 equals P2 V2. Okay, so Charles' law then, if you take out pressure, whatever you hold constant, you just throw it out of the equation. So what we're left with is V1 over T1 equals V2 over T2. Again, this picture with the cylinder, if you have gas at 0.5 liters, that's the volume, 1 atm pressure. And now we're given some extra information. It tells us the temperature is 200 Kelvin. Well, we're holding pressure constant. So pressure is going to be the same here, 1 atm on both sides. But what's going to happen, let's look at what happens if we heat it up, if we heat up the cylinder, the gas. This is actually how hot air balloons works. So I'm going to talk about that in a second. If we heat that gas up, so we double the temperature. Again, we're keeping pressure constant. The volume must increase. Why? Why does that have to happen? Well, what happens when you heat something up? The particles are moving faster and faster and faster, and they're colliding with the walls of the container more and more often. That increases pressure. Okay, so to keep pressure constant, we've got to give it a bigger volume. The more space there is, the less often then they're going to collide with the walls. Keep the pressure constant that way. All right, if you think about a hot air balloon, okay, remember things that are less dense, they rise. All right, remember people tell you if you're less dense than water, that's how you float. Same idea with gas here. What's happening is that the hot air balloon, when you light the fire and you heat the gas up, the gas is moving more and more and more, and then the hot air balloon is expanding. Okay, obviously it's getting full of the gas because the gas is putting pressure on the walls of the balloon. Well, what's happening is that the density, eventually that balloon is expanded as big as it can get. So you got a set volume. And the density of the gas inside the hot air balloon compared to the gas in the atmosphere around the hot air balloon, inside the air balloon, the density is lower. And so that's what causes the hot air balloon to rise because the density of the gas inside drops. You have the same mass of the gas inside the balloon, but the volume has increased as the balloon enlarges. And so that changes the density, lowers the density, and that's why hot air balloons rise. But it's all Charles' law, which is cool. So temperature and volume are directly proportional. So, oops, someone highlighted. They're proportional. So V divided by T is a constant. All right. I don't have a medical example to work here. I just wanted to show you that one with Boyle's law, but I bet you could find one. Next one, Gay-Lussac's law. This one is between the last two properties we have not examined, temperature and pressure. So guess what? We're holding volume constant here. So this is what the combined gas law looks like when the volume is held constant. So now we're not moving the lid on the cylinder. But what Gay-Lussac's law is P1 over T1 equals P2 over T2. So again, whatever is being held constant, you remove from the equation, from the combined gas law. So again, the volume is now fixed. This is fixed. So we're not moving the lid this time. So initially we have a pressure of 200 Kelvin. This time, if we heat it up to 400 Kelvin, what happens to pressure? Well, pressure starting out is 1 atm. Now those particles are moving really, really fast, but we haven't given them any more volume to move around in. So the pressure just increases proportionally. If we double pressure, look, we double temperature, 1 atm to 2 atm. If we were to half or cool down the gas and half the pressure, we would half the temperature, we'd half the pressure. So as one increases, the other increases. So volume and pressure individually are both directly proportional to temperature. As you heat something up or cool it down, volume and pressure will both individually change accordingly. But volume and pressure together are inversely proportional. As you increase volume, you decrease pressure. As you decrease pressure, you increase volume. Okay, so these are proportional. All right. And then you can check, is P divided by T a constant? I didn't even do this on the last slide, but we can always check, right? So 1 atm divided by 200 Kelvin. What number do you get there? And then come over on this side and do 2 atm divided by 400 Kelvin. You should get the same number. If this statement is true, that when we take the pressure and the temperature and divide each other, we get a constant if the volume is not changing. You get the same number on both sides? Nobody's reporting anything. Okay, unless somebody says they don't, I'm going to assume you do. All right, that is the 3 individual gas laws. Okay, Boyle's law, Charles' law, Gay-Lussac's law. They're the same. Good, thank you, Will. Okay, next one is volume and molar amount. So this law is not actually in the combined gas law, but this one is setting us up for the ideal gas law. So the 2 big laws, I know I've introduced a ton here. The 2 main ones I want you to focus on from this lecture are the combined gas law. We're going to work a problem directly with the combined gas law. And Boyle's law, Charles, Gay-Lussac's has set us up to understand that law. And then the other important law, so combined gas law and then the ideal gas law. If you focus on 2 and study 2 for the exam, study problems with these 2. Literally, you can go to the back of the chapter 8, find the section that says problems with ideal gas law and combined gas law, work those problems, okay? But Avogadro's law is setting us up to understand the ideal gas law because there's a property about gases that we haven't looked at yet, and that is their molar amount, okay? So if I have 2 balloons here, a blue balloon and a red balloon, obviously one's bigger than the other. Which one has more gas in it? It's a very silly question. Thank you, Bailey. So this one has more gas. There are more particles, more moles of gas in the red balloon. So obviously, the larger the volume, the more gas that's present. That's all Avogadro's law says. But yeah, so there's my question. How does this look? Okay. Avogadro's law at constant temperature and pressure says that the volume of a gas is directly proportional to its molar amount. Okay, so what you get if we're abbreviating volume with a V and molar amount with an N, the number of moles, it's V1 over N1 equals V2 over N2. Okay. All right. I wanted to also introduce this little abbreviation right here because you might read some problems in the back of the textbook as you work them or in the textbook that say things like this. At STP, the volume of the gas is this. What's the molar amount? Okay. And so you need to know what STP means. So if we're holding temperature and pressure constant, what they've come up with is a standard temperature and pressure that gases can tend to be at. And that helps make some of these problems easier to compare. Okay, like if you're doing research on gases, it's kind of nice to have a standard temperature and pressure you can run your experiments at and make direct comparisons between your experiments, things like that. So standard temperature and pressure of gas samples set to conditions known as STP. So what the standard temperature and pressure are, they're listed right here. Okay, standard temperature is 0 degrees Celsius or 273.15 Kelvin. Standard pressure is 1 atm. All right. Now, what I think is kind of maybe the most important statement on this slide besides the law itself is that at STP, 1 mole of any gas has a volume of 22.4 liters. 1 mole of any, that's a lot of liters. That's a big volume, okay? That is standard molar volume. At 1 mole of any gas at that temperature and at 1 atm pressure will occupy a volume of 22.4 liters. I was kind of surprised when I remembered how big that was. Okay, so again, I haven't worked a problem directly on Avogadro's law, but all of these problems, Gay-Lussac's law, Charles' law, Boyle's law, they work the same way. You will be given 3 of the 4 pieces. So I would give you like a V1 and an N1 and a V2 and say, okay, what is the molar amount, at this new volume condition? Okay, so you'll be given 3 of the 4 pieces. You just isolate the variable, the letter that you're trying to solve for. Make sure your units match. If you have 2 different volumes or 2 different pressures or 2 different temperatures, and plug everything in and solve for the missing piece. All right. So here's a review slide. So this slide is kind of nice because it's everything, all the different laws that we've covered the past several slides on just one slide. And again, the one I want you to focus on is the combined gas law. If we were in person and you didn't have all your notes for exams, I would tell you the one I want you to memorize is the combined gas law. Don't worry about memorizing all the other ones. Okay. I'm forging ahead, aren't I? I have some problems that I really want us to practice and work and get to. And so I'm going to save some time at the end of lecture to go back and practice putting these into play. I'm going to introduce the very last gas law. All right, the ideal gas law. And then we're going to work some problems. Okay, so this is the other important law, combined gas law and ideal gas law. These are the main two. The ideal gas law is different though. How is it different than the combined gas law? It includes the molar amount. Okay, combined gas law is just looking at pressure, volume, and temperature and how those things change. It says nothing about the number of moles of a gas you have. But we know moles of a gas can be important. It changes the volume. So this is the relationship between pressure, volume, temperature, and the number of moles. Okay, so this variable is included in the ideal gas law. So the equation is this. PV, pressure times the volume, equals the number of moles of gas times R. What is R? R is a new constant I'm going to introduce to you. NR and then T for temperature. PV equals nRT. PV equals nRT. So R is a constant whose value and units do not change. If you look up or Google gas law constant, you'll see several different numbers. The number we are going to be using based on the units that we need is this right here, 0.0821. And then, wow, this is the most units we've seen on one number. It's got units of liters and ATM on the top, moles and Kelvin on the bottom. Okay. We saw delta S had 3 units, calories, moles, and Kelvin. This one has 4. Okay, so this one wins, most complicated. All right. And so again, if you look up gas law constants, make sure you're using this one because this has the right units that we need. Other gas law constants may have different units. We want these units. So this is just going to be algebra. I would give you, how could these problems look? We're going to work an example problem, but you'll be given 4. Well, really, we've got 4 pieces that we don't know. Which pieces do we not know? Pressure, pressure and volume, N or T. We always know what R is. R is a constant. So I could give you pressure, volume, and number of moles and have you solve for the temperature. I could give you the volume, number of moles, and temperature and have you solve for the pressure. Okay, I could give you 3 of those 4 highlighted pieces, highlighted variables, and then ask you to solve for the one you don't have. Gabrielle said it. Gabby says, always convert Celsius to Kelvin. That's exactly right. Why? Because you have units of Kelvin in your gas law constant. So you always have to make sure temperature is in Kelvin. So let's actually work this problem down below. How many moles of air are in the lungs of an average person with a total lung capacity of 3.8 liters? Assume that the person is at 1 atm pressure, so they're at sea level, normal body temperature of 37 degrees Celsius. All right, so whoa, where is my question? Some of you are like, I don't even know what to do. Always figure out what the question is asking. It says, how many moles? So you are solving for, what are we solving for? We're solving for N. N is number of moles. That's the first thing you have to do. Figure out which part of the puzzle you're solving for. So before I even start converting and plugging in, I'm just going to rearrange my equation to get N by itself on one side of the equal sign. Can anybody tell me how to do that?
PV over RT.
What we need to do is take PV, good job, thank you, nRT, Cross divide both sides by R and T. So they cancel on this side. Now N equals PV over RT, just like Kristen said. That's the first step. So if you read these gas law problems, and like, what do I even use? How do I know if I need the combined gas law or the ideal gas law? You have to look at what your problem gives you. If it's asking for number of moles anywhere in the problem or it gives you number of moles, guess what? That's ideal gas law. Because remember, that's the only one that has number of moles in the equation. If it doesn't say anything about number of moles, it could be a combined gas law problem. All right, now we're going to plug everything in except for the fact that I see temperature is in Celsius. And as Gabby said, we got to convert that to Kelvin. So really quick, 37 degrees Celsius plus 273.15 is going to give us 310. Is that right? Now I'm ready to plug everything in. So I like to go through and highlight. Here's my pressure, 1 atm. Here's my new temperature. And here's my volume, 3.8. So those 3 blue highlighted pieces plus my R all get plugged in on the right side of the equal sign. So N equals P. What is P? It's 1 atm. And does atm match what is in my gas law constant? Right there. Yes, it does. Okay, if it's in PSI or if it's in millimeters mercury, you've got to make sure it's in atm. Why? Because you've got to match the units that are on R. Or this problem, you get the wrong answer every time. All right. So what is my problem to me? P times V. Okay, so in the top here, I've got P times V. So my volume is 3.8 liters. Hold on, is liters what we need? Or do we need to convert to another unit of volume? Well, look at R. Okay, liters is good. We got liters in R, so liters is fine. We are looking for the moles part. And on the bottom, we're going to plug in R, 0.0821. Okay, I know. You're just like, can I leave off the units, please? No, you can't. You have to write everything. So it's L times ATM over mole Kelvin times Kelvin. And then I multiply R times temperature, which my new temperature was 310.15 Kelvin. So that's times R. So there's R. Helps if you put it in parentheses sometimes. This is my P, that was my V, this is my R, and this is my T. Okay, I encourage you to, in your calculator, put it all in brackets, do 1 times 3.8, and then on the bottom do the 0.0821 times 310.15, divide those two. All right, I'm seeing in the chat that N, the number of moles, is equal to 0.149. So, how many moles of air are in your lungs? Very, very small amount. 0.15 roughly moles of gas, very little. And that is yet enough gas to fill your whole body with oxygen and all the things you need. All right, so that's combined gas law and ideal gas law. Wow, we're doing superb on time. I actually want to skip over partial pressures for a minute. We may indeed come back to that. I had some fun stuff to talk about. I want to find a combined gas law problem. And I have a lot of practice problems down here. Do you have these slides at the end of your lecture slides? Do you have these practice problems? Okay, so we're going to do some practice. And then if we have time, we may go talk about the last few things from the lecture. Here, a gas has a volume of 300 milliliters at 300 millimeters of mercury. Did I say millimeters? 300 milliliters, 300 millimeters mercury. What will the volume be if the pressure is changed to 500 millimeters mercury? So again, this is obviously a gas law problem, some kind of gas law problem, because we're talking about a gas. How do I know what law to use here? Anybody know actually what law we should use to solve this?
I don't know the name of it, but there's only volume and pressure listed, so it's gonna
Boyle's.
be VP.
Only volume, that's exactly right. So for those of you that are sitting here like, what the heck do I do? Look at what the problem gives you. Let's highlight it. That's a volume, that's a pressure, that's a pressure. So just go through and label these. This is V1. It's the first volume is given, so I'm just going to call it V1. This is P2. How do I know this is a pressure? It's a units of pressure. We introduced a lot of units of pressure, and that's millimeters mercury is one of them. Oh, why did I write P2? This should be P1. P1, sorry. And then the next pressure is P2. So here's what we see. It's exactly what, I don't know who said it, but they were right. Only volume and pressure is given. So we're going to, again, if you just memorize the combined gas law, P1 V1 over T1 equals P2 V2 over T2. You don't have to go through and be like, okay, crap, is this Boyle's, Charles, or I don't know. Just know the combined gas law, see that you have nothing about temperature in here, so just get rid of temperature. Okay, this is the law we use right here. And yes, it
And
is
if
Boyle's
that
law.
if that confuses anyone, like whenever I was doing the homework, I would get confused sometimes. And so like I would just put 1 in. If you just put 1 in for the one that you don't know or like is needed.
Yeah, you can do that. Just plug in 1 for temperature. That works as well. All right, so this is the law you're supposed to use. Thank you, Bailey. Here we go. So we're just gonna plug these in. First off, one thing I'm gonna check before I just plug everything in. Do my units of pressure match? Yes, they do. If your P2 is in like PSI or ATM, you just need to convert one to the other. I don't care which one. Just make sure your units on pressure match. So let's plug these in. P1, you got 300 millimeters Hg times V1, which is 300 milliliters, equals 500 millimeters Hg times V2. So we're looking, because it says, what will the volume be? That's asking for V2. So you just divide both sides by 500 millimeters. And it cancels on this side. And now you just do 300 times 300 divided by 500. Conveniently, millimeters of mercury go away, and all you're left with is milliliters. So that's going to be good because your volume will have units of milliliters. What do you guys get?
180.
180 milliliters. Okay. Okay. All right, questions on that one? This next problem, again, just start with the combined gas law. You're given a volume, so that one you're going to label V1. You're given a temperature, this is T1, and you're given another volume, so that's going to be V2. What is the new temperature? So you're looking for T2. It says report the new temperature in degrees Celsius. Now let me tell you something. All the gas laws have to be worked in Kelvin. So this is going to feel very redundant, but you have to convert the temperature to Kelvin, work the problem, and then here it says report it back in Celsius. Okay. So once you get your answer, you're going to have units of Kelvin, and then you just convert it back to Celsius. Okay, you cannot work it in Celsius. So you'll do, what's the combined gas law? P1 V1 over T1 equals P2 V2 over T2. We don't have anything about pressure here. So you just get rid of pressure. plug in a 1 like Bailey said, or just erase it all together. So this is Charles' law. V1 over T1 equals V2 over T2. And I see that my units on my volumes, my two different volumes match, which is good. To plug in this temperature that I'm given, the 45 degrees Celsius, I'm going to convert that to Kelvin. So it's 45 plus the, well, degrees Celsius plus 273.15. Is that 318? I think so. And that's Kelvin now. So now we're going to plug in 350 milliliters. That's V1 over T1. Okay, so this is my new T1. So it's over 318.15 Kelvin. That equals V2 over T2. Oh, we need to plug in V2. So that was 400 milliliters. Okay, I'm glad we're working this problem because a lot of people are going to mess this up sometimes. They'll just try to move the 400 milliliters over, and once you got T2 by itself, you just solve for that. You can't do that. T2 is in the denominator, okay? It's in the bottom down here, all right? We can't solve for 1 over T2. You've got to solve for T2. So how do you do that? My favorite, quickest shortcut way to do this is literally flip the whole equation, okay? Just if you flip both sides, you've done the same thing to both sides. You can do that. So literally just do 318.15 over 350 milliliters equals T2 over 400 milliliters. You flip the whole thing on its head. Now we got T2 in the denominator. Now we can move over the 400 milliliter part, okay, and solve for T2 by itself. That's the quickest way to do it. If not, you got to move like 3 or 4 variables around and it gets more complicated. So I'm actually going to slide this whole thing down here. Now you just multiply both sides by 400 milliliters. And cancels over here. So to solve for T2, you'll do 400 times 318.15 divide by 350 milliliters. And then we'll convert it back to Celsius. What do y'all get? Volume went up, so temperature should go up because remember they're directly proportional. So we got that T2 equals 363.6 Kelvin. And Bailey already put it in Celsius for us. You need friends like that in your life. So just go ahead and go the extra mile. 90.45 degrees Celsius. All right. So that was technically a Boyle's law and a Charles law, but again, just worry about the combined gas law and then take out the piece you don't need. How are we doing? What do we got? Well, that's a fun one. That's a good problem. Do you like these scanned? These are ancient. These are scanned copies of the hard textbook. So these are problems with Gay-Lussac's law. You can literally go find these in the textbook. Good problems to work. Examples of combined gas law. Terribly hard to read because they're right on the spine of the book. I think that's all the problems I have here to work. I want to work one combined gas law problem because we've yet to actually plug in everything and work the full thing. And then we'll see where we are on time with that. So can you guys even read this? This is 8.62. It says a gas has a volume of 2.84 liters at 1 atm and 0 degrees Celsius, which is, let's just go ahead, that's just 273.15 Kelvin. At what temperature? So let's go through and label. This is V1. This is P1, this is T1. So what temperature? We're looking for T2. Does it have a volume of 7.5 liters? So that is, this is V2, and 520 millimeters mercury. This is P2. So how do I know this is a combined gas law problem? Because look at all the stuff I'm given. You've got 6 different variables here, and you're given 5, and you're looking for the 6th. And it says nothing about moles of gas in it, right? You don't see moles of gas anywhere in it, so that's a key to you that this is not an ideal gas law problem. This is combined gas law. If you can go through and label like we just did, 2 different volumes, 2 different pressures or whatever, and you're looking for this 6th term, that's combined gas law. The other thing I notice is that we've got ATM on our first pressure term, but we've got millimeters of mercury on the next pressure given. So here's an example, like what I was saying, where you're going to have to, yep, Gabby put it in the chat, convert either ATM to millimeters of mercury, make them match, or millimeters of mercury back to ATM. Let's take millimeters of mercury, convert it to ATM, because I always like working with those nice, easy, simple ATM numbers. So I'm going to scroll up. I got some white space up here. You can still see the problem at the bottom of the slide. So this is what we got. P1 V1 over T1 equals P2 V2 over T2. There's our law. And a couple of things we need to do. One, convert P2 to units of ATM. Why? So that it matches the pressure units on P1, that first pressure condition given. So to do that, we got 520 millimeters mercury. How do I convert this to ATM? You guys remember? We actually did pressure conversions way earlier in lecture. We need to know, we're going to cancel millimeters mercury. Whoops. And convert to ATM. So I just need to know what numbers go here. How many millimeters of mercury?
760.
Equals how many ATM? Yep. Should be 1 ATM. So you just plug these in. You can go look at the slide earlier from lecture, okay, if you're not sure. So we're going to cancel millimeters mercury, convert to ATM. So we haven't even started the problem yet. We're just getting the units and things the way we need it. Like 0.6, 0.7, somewhere in there. Anybody got it?
0.68.
All right, 0.68 ATM. All right, so this is our new P2. This is the one we'll use when it's time to plug that in. Okay, so now we're just going to plug everything else in. So V1 is 2.84 liters times our P1, 1 ATM. I know I mix these up. Usually it's P1, V2. It doesn't matter as long as you're multiplying those two on the top, okay? T1 goes on the bottom. What's T1? We already converted it to Kelvin. It's 273.15 Kelvin. And that is equal to P2 V2 over T2. All right. So P2 is, we convert it to ATM. It's the 0.68 ATM times V2 down here in the problem is 7.5 liters. And that is all over T2. Oh no, what I'm solving for is in the denominator. It's not on the top. So what do we need to do? What did we do last time we had this issue?
Flip them.
Flip the whole problem, okay? So if I flip everything, you should get 273.15 Kelvin over the 2.84 liters times 1 ATM. That equals now T2's on top, 0.68, whoops. I can write or speak faster than I can write. So as I'm speaking, I start to write what I'm saying in all the numbers. 7.5 liters. Okay. So now I didn't really leave myself a lot of space. You need to cross multiply both sides of your problem, right? Here's why I love iPads. Need to cross multiply both sides of my equation by the 0.68. I did it again. Times the 7.5 liters, okay? Cross multiply both sides. And cancels all that out over here. So combined gas law problems, they're not all that easy either because you just have so many different pieces and so many different units. But this is how you solve this one. So we're going to do 0.68 times the 7.5 liters times the 273.15 Kelvin. This is all multiplied up here. And then you're going to divide it by, I would love to put these bottom parts in parentheses, 2.84 times 1. And that will give you T2. Anybody get what temperature the gas would be at? 490.5. 490.5, and this is Kelvin. So anyways, I need to update these slides down here now that we have electronic copies of the textbook. That's an example of a combined gas law problem. Okay.